So this chapter is dedicated to torsion. So first of all, we go with the concept of pure torsion, and then we'll be going into the concept of shafts in series and the shafts in parallel. Okay, so basically, first of all, we should know what is the difference between a torque and torsion. So what is the difference between torque and torsion? First of all, let me explain you regarding the torque. Okay, so that we can have some basic idea. So once we have the basic idea of torque, we can easily understand what is the meaning of torsion. If any pulley is there or any member is there, it is fixed about some point. That means it is pivoted about this point. It can rotate about this point here. If you apply a force about the center, it will not cause the rotation. But if you apply a force about some other point here, about some perpendicular distance as r here, so it will cause some turning effect. Understand? It will cause some turning effect here. So it is acting in this direction here. So to know the direction of rotation here, you have to do one thing. You have to put your fingers from center along the radius here, the perpendicular distance here, like this or like this one here. After putting like this, you have to curl your fingers in the direction of the force. So force along this direction here. When you curl in this direction, it is showing that your thumb will be pointing into the board and your fingers will be curling in clockwise direction here. So this torque value or the turning effect of the force R into F is clockwise rotation here. Understand? Generally, we take the rotation as counter-clockwise torques as positive here and clockwise torques as negative here. We follow the sign convention here. Because if you take the coordinate system in this way, x-axis like this and y-axis like this, if you are curling your fingers from x to y, anti-clockwise sense, your thumb is pointing in z direction, positive z direction here. Understand? So that's why taken as positive here. If you are curling in clockwise direction, your thumb will be pointing into the board, which is nothing but negative z direction. So we take the clockwise couples as negative direction here, negative sign here. Understand? So this is a basic concept of torque here. So whenever I'm asking regarding the torque or moments, because we're going to use the concept of moments in a very, very extensive way in the next chapter, in the shear force and bending moment diagram. If you can't understand which one is the clockwise moment, which one is the anti-clockwise moment, so you can't understand the concept very thoroughly there. So whenever you would like to find out the direction of rotation for the moment or the torque, you have to go in this way here. I'm explaining once again, kindly have some clarity here. So you take the perpendicular distance of the force here, you draw the perpendicular to the center here. From the center, you put your fingers along that distance there, either like this or like this one. And then curl your fingers in the direction of the force. So here the force is in this direction, so I have to curl in this direction here. If the force would have been in this direction, I would be curling in this direction here. So when we are curling in that direction, we will be coming to know the direction of rotation because of the applied amount of force there. So the turning effect is quantified in terms of magnitude and also direction there. So direction is in terms of clockwise or anti-clockwise. Magnitude is given by this value here, R into F here. Got it? Clear to all? Understand? So this is the concept of torque here. Okay, so torque, we know that if any body has to be in equilibrium, it must not be experiencing any motion, that means linear motion and also angular motion. That's why in dealing with 2D loading cases, we take the equilibrium equation as sigma fx is equal to 0, sigma fy is equal to 0 and sigma mz is equal to 0. As the forces are in x and y directions, they will cause the rotation in z direction, about z direction. I am taking the moment mz is equal to 0 here. So understand, if the forces are in y and z direction there, then the moment will be produced along or the moment will be produced about x axis there. Understand? So if a pulley is there, it is x-axis here, it is y-axis here. The force components, the force is on the xy plane here. The force is on the xy plane here, but is rotating the pulley about z-axis. So this moment given by the force F, R into F, whichever you're gonna got here. R into F is nothing but moment about z-axis here. Okay, clear? This is the concept here. But now, when we know that a body cannot experience stress when it is not in equilibrium. Okay, the body has to be in equilibrium to experience the stress, because the stress is actually resistive force per unit area. That resistive force will be produced inside the material only when it is in equilibrium. Understand? So if you create any rotation like this, it will not be experiencing any stress at all. Clear? So what I have to do is I have to cancel that torque. Understand? Just like in a linear cases there, if a force is acting in x direction, positive x direction here, so to create an equilibrium case, I have to apply equivalent opposite force in the negative x direction here. Understand? Equivalent opposite force in the negative x direction here. So this body will be in equilibrium and this will be experiencing the stress. In the same way, if any shaft or any torsion member is there, what I have to do is, if it is experiencing a anti-clockwise torque in the one face, on the one side here, anti-clockwise torque here, I have to create reverse torque on the other side, in terms of same magnitude here, or the reverse thing can also occur here. So here, if it is in the clockwise direction, here I have to put it in the anti-clockwise direction here. Okay, so you see that over the length of the shaft here or the torsional member here, basically, it's not compulsory every time it must be using the shaft here, but concepts are very simple to understand using a shaft here. So what happens is, although on the one side I'm trying to rotate in anti-clockwise sense, this will be trying to cancel that effect in this one here. So when the material is when the material is in equilibrium here, we see that some twisting is occurring, or the material is experiencing some stress inside the material there. Understand? So this phenomenon is called as torsion here. Understand? So these two cases are nothing but torsion cases. Nothing but the torsion case here. So torque is the turning effect of the force, and torsion is the torque loading case in which the stress can be produced here. That means the torque must be applied in which way so that the metal will be experiencing the stress here. Understand? And another thing which you have to always remember is, here we have to see that this is the length direction or x direction, you can take it here, or longitudinal direction here. So the arrow marks, both of them, this arrow mark and this arrow mark, are longitudinal directions here. So to create torsion, the moment must be acting about longitudinal axis here. Understand? To create torsion, or I can write down in one way, in this way here, torsional member. So torsional member may not be a shaft, or may not be a rectangular section or any section, okay? But if it is experiencing moment or the turning effect on a plane about the x-axis, the turning moment is about the longitudinal axis here, we call this member as a torsional member here. The member which experiences moment about longitudinal axis. The member which experiences moment about longitudinal axis is called as torsional member. Okay, so please copy this one, make it fast. Instead of making one type of torque and reverse torque on the two sides there, to accomplish it very easily, generally apply torsion on a shaft which are attached to a fixed support, just like the diagram there. So if you apply torque there, as the rigid support is there on the left side, or some fixed support is there on the left side, so what happens, it will be automatically creating a reverse torque and causing the member to experience torsion. Understand? So to create torsion, we have to apply the forces in that way, as it is shown in the slide there. From that slide, we can have a basic idea that the force is acting parallel to area of cross section. So we can say that the torsion of the shaft will create shear stresses inside the material. Understand? So the torsion of the shaft will be experiencing shear stresses. Please kindly note that part. As the force acts cross section, torsion creates shear stress here. Yeah, couple. See here, actually, there is a difference between torque and couple. Okay, basically, generally we can take for a torque and moment to be same. Okay, torque and moment to be same here, but there is a difference between couple and a torque, because couple means two equal and opposite forces separated by a distance. Understand? Please copy this one. Once you're done with this, I will explain regarding the difference between couple and a torque here. If you would like to know why the force is acting parallel to area of cross section, dear Ankit, you see the diagram in the slide. It is very clear. To create a torque about that axis, force must act on the plane itself. See the diagram on the slide, you can understand that. So torque means, first of all, I will tell you regarding the torque here. So torque you have already known here. So if, for example, a pulley is there, if single force is acting here, so we extend the line of action of force, we find the radius. So torque will come as R into F simply. So couple means basically two equal forces, two equal and opposite forces actually, So for example, just think that a force is acting on a body in this way, another force is acting in this way here. Both the forces are same in magnitude, but directions are different, and the perpendicular distance is given by some r here. Okay, so perpendicular is given by r here. Understand? So in this case, couple is equal to given by r into f, simply. Okay, so you can apply the same thing to get the clockwise rotation or anti-clockwise rotation here also. You take center as this part or this part. You take center as this part here, and this is the perpendicular distance for this force here. So you put your fingers like this or like this. If you put like this, you can curl it. It is coming as clockwise here. You can go with this one also. If you go with this one, this is the center here. This force cannot create a couple here or torque here basically, or a turning rotation, turning effect here. So from this center, you put your fingers along the radial distance r here, like this. Like this or like this. So I'm putting it in this way here, so that I can curl it into the along the direction of the force here. It is clockwise here. So in couple, two forces will be there, but in the torque, we require only one force there. Understand? So basically, like in this chapter of torsion, we're going to see the effect of all of them. That means like torque, that means like the torsion can be created either by the couple, okay, because ultimate thing is the turning effect here, either by the couple or the torque or the moment there. Everything will be same itself here. So if you take that one, the radial distance is d, the distance between the two forces is f here, but that's actually shown as a couple there. Understand? The same diagram I can show you in this way also. So the diagram given in the slide is like this one here. The shaft is experiencing the forces in this way here. An upward force F and downward force F, both are separated by a distance d. So torque or couple is actually here, couple is acting here. Couple is equal to given by F into d here basically. Or you can take it in this way also. You take the center. You take two forces, different forces here. You take the center here. So torque because of this force is equal to given by F into d by 2. Okay, anti-clockwise sense here. If you take this one also, F into d by 2, anti-clockwise sense. So total torque is equal to given by F into d by 2 plus F into d by 2. So total will come as F into d here. Understand? So the torque can be created on the shaft in other way also, or this torsion member in the other way also. So if I apply some force F like this, okay, the radial distance is r. Okay, so here the torque or the torsion will become F into r here. Understand? Clear? So this is how you're going to take it. Okay, and regarding the sign convention, I told you regarding the sign convention here. The sign convention we follow is counter-clockwise torques are taken. Torques means I am generally using the word as torque. That means it is same for moment. You can use the word as moment also. You can use the couple also. If two forces are causing this thing here, understand? So counter-clockwise torques or moments or anything are taken as positive, and clockwise negative. This is a sign convention here. Understand? This is a sign convention here. Okay, clear? So we'll go with the remaining part of the torsion topic. Okay. So the assumptions are here. Basically, when you do the torsion, what happens is it will be undergoing twisting. Okay, it will be undergoing twisting here. So that means initially if the point is at here, after the torsion here, this point will be shifted to here. So it will be becoming like this one here. So basically what happens is, if you see from this side, it will be, initially it is like this, and after that it will become somewhat like this one. Okay, so it will be experiencing some twisting here. So when it is experiencing like this, actually the plane which was initially perpendicular to the length here, circular plane here, it will become somewhat irregular like this one here. Okay, so in this assumption, in this chapter here, we take the assumption that this effect is negligible. We neglect this effect here. That means we consider, even after twisting also, the planes are perpendicular to the length. All the cross-sectional planes are perpendicular to the length here. Understand? And other thing is, when it's undergoing twisting here, there is some axial strain. That means the change of length or expansion of the length or compression of the length here. So we neglect these effects also. So whatever twisting is occurring here in these cases, or whatever the deformation is occurring because of this twisting here, we neglect those effects here. So one thing is regarding the circular plane here, which should be considered to be perpendicular to the length of the shaft here. And the second one is no linear strain must be there. Okay, or no linear strain is there in the axial direction basically, and also radial direction there. Understand? That means if due to twisting, if there is any change of diameter, so we should not be considering that part. Understand? This is the meaning of these two assumptions here. Understood? So now we are entering into the main part of this chapter here, the torsion equation. I'll give the partial proof for this equation here. If you take a shaft which is of certain dimensions, diameter, length, etc., and all these things there. So the shaft is like this. You're basically going with shaft to explain to show you regarding these torsion equation and all these things there. Okay, but these expressions are valid for any type of member. Only necessary condition is it must be experiencing torsion about the. It must be experiencing torsion means it must be experiencing some moment about the linked axis. About that axis, it must be experiencing some torsion. That's the main requirement here. Understand? So if this is the shaft here, which is experiencing torsion. So initially the area is initially the point is here, but it is experiencing of anti-clockwise torque and the positive anti-clockwise on the positive torque here. So what happens is this point will be shifted to from this position to this position. So if you take this point as A, this point as B here, initially the point is at B, but what happens is it will be twisted to, it will be shifted to the point B dash here. So we see that this is the angular change. So we give this one, this is the angular change here, so we give this one as gamma because this is the shear strain which is occurring in this case here. Because the application of torque in this way, this is the angular change here, so we denote the angular change by shear strain here, so we show it as gamma here. Understand? Now we apply, we see some angular displacement on this plane also. So from this one you can easily say that there is some relation between gamma and theta here. Understand? Let's take the length as L and it is R here. Let me show you how can I get the value of B dash. B dash can be written as, the arc length B dash can be written as gamma into length. This can be also written as R into theta here. Understand? R into theta here. So it's actually, I will take it as capital R here. Capital R here. Understand? Gamma into L is equal to R into theta here. But you have the relation that shear stress by shear strain is equal to rigidity modulus. So this implies gamma is equal to tau by G. If you substitute this one in this equation, we'll get tau L by G is equal to R into theta. This implies tau by R is equal to G theta by L. This is the formula here. Understand? This is a partial formula here, and the remaining part of this formula is T by J here. So I'm not going to give the proof here, but understand? So T by J is equal, but I'm giving you the formula here. So T by J is equal to tau by R is equal to G theta by L. So where J is the polar moment of inertia. That means moment of inertia about the longitudinal axis here. So J is moment of inertia about longitudinal axis here. Understand? So although this formula is given with respect to the maximum radius R here, okay, so this thing will be same for any radius here. But only difference is the shear stress is proportional to R here. So shear stress variation will be 0. Shear stress value will be 0 at the center part. But as going on to the extreme fibers here, so we'll be experiencing higher value of shear stress here. So shear stress is varying linearly with respect to the radius of this thing here. So in a general way I can write down this shear stress formula or basic torsion formula as T by J is equal to tau by R is equal to G theta by L. Now the most important one. The most important which we have to use is, understand here is, here we understand that the meaning of this equation is, if I create a torque value of T, if I apply a torque of T on a member which is having polar moment of inertia as J, and the point at which I would like to find out the shear stress is given by R. That means the distance of the point from the center distance. So if you are finding out that R is equal to capital R is equal to R by 2, that means small r is equal to capital R by 2, it will be at the center here. Understand? Center of the radius here. So like that. You can find any angle, any value of radius there. So in this one, the meaning is if I create a torque value of T for a member which is having a polar moment of inertia of J at a distance of R, the shear stress is given by tau. Okay. In other way, for a length of L, the angular twist which is produced because of torque applied T is equal to given by theta here. That means here you have to understand that the tau values and theta values are dependent parameters. They are dependent on the value of torque applied there. So torque is the deciding parameter here. So that's the independent parameter. So that is giving rise to shear stress as tau and is giving rise to angular twist as given by theta here. Understand? So because based upon this definition only, I am going to give you one question in the coming slides. So there you have to find the answer very correctly there. If you don't understand this formula correctly, the meaning of this one, you'll be ending up getting a wrong answer. Understood? So please copy this one here. Dear Manish, I have already completed Mohr circle concept in the second chapter. You can go to the recorded lecture for the Mohr circle concept there. Okay. So listen carefully here. If you take a member and which is experiencing torsion here, so before the experiencing of torsion, the point A and B are along the length here at this particular locations. But due to the twist produced because of torsion application, B got shifted to B dash. So B dash can be written as gamma into L here, or it can be written as R into theta also. Clear? So where R is the maximum radius here, or the radius of the shaft here, radius of the member here. So tau by L, actually tau by gamma is equal to G here. That means like shear stress by shear strain is equal to G here. So from this one you'll get this relation. Okay, this one. So you substitute in this one, you'll be getting this relation here. So this can be written as like this. Understand? So this is a half derivation here. Remaining part of the formula is given by T by J is equal to the remaining part here. Tau by R is equal to G theta by L. So although this formula is given only with respect to capital R, this can be written with respect to small r also. That means we can find out the stress at any point inside the material at a distance of R from the center there. So if you would like to find out the maximum stress inside the material, you will take the maximum value of R, that is nothing but the capital R there. That's the only difference here. Understand? So the meaning of this statement is, if I induce or if I apply a torque value of T, then the material of the shaft at a distance of R from the center will be experiencing a shear stress of tau, and the angle of twist, the angle of twist that is occurring at a length of L is given by theta here. For a shaft which is having a metal property G here and dimensional properties as J and J value here. Am I clear to you? So is it clear everybody? So please copy this formula here. So based upon this we go with some further terms which are arised in this torsion equation, and after that we will be going with some numericals here. Okay? Okay? So next one. So next term is polar sectional modulus. It is denoted by Z suffix P here. So please write down the title, polar sectional modulus. And what is the significance of this? The polar sectional modulus ZP is given by J of the member by R maximum. Understand? J by R maximum here. So actually we have the formula T by J is equal to tau by R here. So if you would like to find out the shear stress at the maximum radius, so this will become like this. So T is equal to given by tau by Z maximum. As ZP, not Z maximum, it is ZP here. As ZP is just depending upon the dimensions of the shaft or dimension of the member, because J is depending upon the diameter of the dimensions of the member here, and R is also depending upon the dimension here. So Z is depending upon the dimensions. So we see that the shear stress induced inside the material is, for applied torque here, shear stress produced inside the material is inversely proportional, shear stress produced inside the material is directly proportional to the ZP here. Understand? Just a minute. Sorry, this is wrong here. Tau is equal to T by ZP here. Tau is coming as T by ZP. Tau is equal to coming as T by ZP here. So this equation says that for a torque value which is applied as T here, the shear stress induced tau is inversely proportional to ZP. So tau inversely proportional to ZP here, and we expect the stress inside the material to be as less as possible. So we have to select the member because it's just depending upon the diameters and all these things here, dimensions here, geometrical thing only, nothing related to material also. So if you would expect lesser value of stress to be induced inside the material, you have to select the member which is having maximum value of ZP, based upon the dimensions which are suitable there for the designing parameters, designing situations there. So you have to select the correct value of ZP, which is as more as possible. So more is Z, lesser will be the shear stress here. So that is the significance of polar sectional modulus here. Understand? So from this result itself, we'll come to know in future that like if you have some amount of material with us, so it's better to make a hollow shaft or a solid shaft. Okay, so you can decide like which one is more preferable to carry some value of torque or to undergo some torsion. So which is the better one value? So that result will come to know in the last part of the chapter. So you have to wait till then. Understood? So next one, torsional rigidity. It is simply the product of G and J. Torsional rigidity is given by product of G into J. Rigidity modulus into J here. Torsional rigidity. Please copy this one. Torsional rigidity G into J. Okay. So next one, torsional stiffness. Now torsional stiffness. So actually we have the formula T by J is equal to G theta by L. So T by theta is called as torsional stiffness. It is given by Gj by L. So it is equal to denoted by Kt. So T by theta is equal to Gj by L. So this is the formula here. So please copy the both of them. So once it is over, we'll go into the next part. So pure torsion, a pure shear loading case. I hope you people know regarding the values of J. For a circular shaft of certain diameter D, so J is equal to given by pi d power of 4 by 32. Okay, if you have a hollow shaft like this, so which is having internal diameter as D1, outer diameter as D2 here, like this one. So J is equal to given by pi by 32 whole into D2 power of 4 minus D1 power of 4. So I hope you people know regarding all these formulae here. Understand? So if you apply the same form, using this value and get the value of shear stress in this case for a solid shaft, so T by J is equal to tau by R, and where R maximum shear stress will be given as 16 T by pi d cube. You substitute the value of J. Okay, so we substitute the value of R also. You get the tau value as 16 T by pi d cube for a solid shaft here. So solid shaft here, hollow shaft. Understand? Please copy them. I know that moment of inertia is represented as I here, but in this case, we're gonna in strength of metal subject we're gonna use two moment of inertias. That means one moment of inertia which is about the axis, about the longitudinal axis, and other moment of inertia about the transverse axis. Clear? So we're gonna use the longitudinal, the moment of inertia about longitudinal axis in this torsion chapter, and the other one in the bending chapter there. So to distinguish between the both of them, instead of writing as IXX, IYY or something like putting suffixes and all and getting confused here, so this one is denoted by J here. Okay, so the moment of inertia which is calculated about the axis of rotation or the longitudinal axis is called as polar moment of inertia. So we denote the polar moment of inertia by J and the other moment of inertia by simply as I there. That's fine. Okay then, let's go ahead here. Pure torsion is a pure shear loading case. I'm going to show you that pure torsion is actually in fact a pure shear loading case only. So pure torsion. Okay, so let's assume a circular shaft is experiencing torsion here. Now in this case, I will take a section at some particular distance here like this. Okay, at this section here. Okay, I will take it in this color here. Okay, this section here. Now, when I am experiencing, when I am showing you, when I am taking care of this torsion here, when I am applying torsion here, it is twisted in the anti-clockwise sense and it is twisted in the clockwise sense here. So, what happening is, if you take the two members independently, or if you consider them to be independent here, we see that there is some like contact occurring between them. Or in other way, if you take the both of them as two individual sections here, both are cut taken as a shaft here like this, and I cut it into two pieces and I joined like this. Okay, so just join them like this one here. When I apply a torsion like this, what happens is basically this part is actually sliding over the other parts. Understand? So that means if you take the free body diagram for the both of them, you're gonna get in this way here. So after slicing off like this, so this part will be having like this one, and other parts. Okay, so this is experiencing shear stress here. So the shear stress I'm denoting it by tau in this way here. So the force will be, the forces on these two areas are making action reaction pairs. So if you divide by the forces by area, you'll be getting the shear stress here. So anyhow, shear stress also will be taking action reaction pairs here. Understand? You got this in this way here. Now in the same way, if you do at some other section, what I'm gonna get is, that means if I cut it like this and separate the two members in the same way, what I'm gonna get is the diagram in this way. Okay, the same thing here. So it will be experiencing shear stress like this, tau, and it will experience shear stress like this one here. Understand? So let's forget about these two things here. Let's concern about this part itself. Understand? If you take only these two parts here, okay, we take only these two parts here. and you take the coordinate system in this way. That means x-axis along the length direction, y-axis in the vertical direction, z-axis along this direction here. Understand? Now, in this one, if you do the stress analysis, just like we've done in 3D loading case, slicing of positive x plane, slicing of positive y plane, positive z plane, and all these things here, and if you take an element, small element in this way, according to this coordinate system here, inside the material, so you're going to observe that there is only this shear stress is coming here, okay, and the other one here. So this is shear stress tau, this is also shear stress tau. Understand? So this is on positive x plane along y direction. Okay, this is on negative x plane and negative y direction. So x, y here. So tau x, y here. Understand? Anyhow, tau x, y is there, means like although we are not showing it here, tau x is also there here. Okay, so for this element, if you draw the stress tensor matrix, it will come as simply 0, tau xy, tau yx and 0. Only these values are there. Understand? Only these values are there here. Okay, so anyhow tau xy, but so we have tau xy value is equal to tau yx here. So this simply so anyhow these two matrices shows that this pure torsion case is simply a pure shear loading case here. Understand? It's a pure shear loading case here. Okay. So for pure shear loading case, you know maximum normal stress sigma 1 is equal to given by can I tell you what is the value of maximum normal stress in this case? I hope you will remember the answers here, or you can calculate by using the values there. Sigma x, sigma y, tau x values are there here. So for pure shear loading case, tau is equal to sigma 1 is equal to given by tau, sigma 2 is also given, it is given as minus tau, and tau max is equal to given by tau here. Understand? So this tau is nothing but the formula whatever you got it there, because whatever shear stress we got it tau occurring inside the material here. So it is, if we got it easily, we got it by using the torsion equation itself. Understand? So from that you can easily calculate there. Okay, so tau is equal to, for a solid shaft, 16t by pi d cube, as it is not same for all the members because it depends upon the geometry there. So I am giving an example. So for a solid shaft, this is for solid shaft here. If you take a hollow shaft, it will be changing again once again. Understood? Clear? So I have already explained regarding torsion of hollow shafts there. So just only thing is the J will be changing. Clear? If it is over, I will just brief it up regarding torsion of hollow shafts, and we'll be going into the next part. For your understanding purpose, I am showing you here. We have the formula T by J is equal to tau by R. For a solid shaft, I told you J is equal to pi d power 4 by 32. So it will become 32T by pi d power of 4 is equal to tau by R. R is equal to, maximum radius is equal to d by 2. So d by 2 here. So if simplify this one, we will get tau is equal to given by 16t by pi d cube simply. Done? Okay then. What happened? Many people are sleeping, I guess. I told you people to ping in the chat box once it is completed. Nobody pinged me. If you are a home gate student, tell your mom to make tea. Understand? Okay then. So torsion of hollow shafts here. So let's take a hollow shaft like this, which is having internal diameter of di and outer diameter as do. Okay, so for this case, J is equal to given by pi by 32 into d outer power of 4 minus d inter power of 4 here. Understand? So in this case, you have to apply the torsion equation. T by J is equal to tau by R here. So actually in every case, we are actually concerned of, in fact, we are concerned of finding out the maximum shear stress. So we know tau is will be proportional to R. So if from center, if you are going on finding out the, if you are interested in finding out the maximum shear stress, so you have to go to the fiber or go to the point which is farthest from the center there. Okay, so if you are going to the nearest point, it will become a lesser value of shear stress there. Okay, so for tau max, R is equal to R max. Understand? For tau minimum, R is equal to R minimum there. So in solid shaft there, basically we know that R minimum is equal to 0. So only tau max will be there. Tau minimum is equal to 0 there. But in this case, R minimum is not equal to 0. It's di by 2 here. R max is equal to d naught by 2. So maximum shear stress tau max will be given as this value here, torque into d outer by 2 whole by pi by 32 whole into d outer power of 4 minus d inter power of 4 here. So basically we are going to get the answer like this one here. So 16t d naught by pi of d outer power of 4 minus d inter power of 4 here, right? 16. So 16 t d naught by pi of d outer power of 4 by d inner power of 4 here. So if you'd like to know the tau minimum value, so you're gonna get you're gonna take this value as d inner here. So 16 t d inner diameter by pi of d outer power of 4 minus d inner power of inner diameter power of 4 here. This is how you're gonna get the answer here. I told you that the formula is actually valid for irrespective of the shape of the dimension, shape and dimensions of the component. Simply it is experiencing some torsion. That means it must be experiencing some moment about the longitudinal axis there. It will be experiencing torsion. So this formula is valid there. Understand? Your torsion member may be even a rectangular bar also. Okay. So further also just get the value of J and get the value of extreme fiber which is in the farthest from the center point there. So substitute the values, you can get the answer. But most of our questions, 99.9% questions are based on the shaft itself, either hollow shafts or torsional shafts. This shouldn't be creating any problem at all. So everybody clear regarding this concept here? Okay then, next question. Come on. I told you that in this question it's given that a long shaft diameter is subject to a twisting moment of T at its end here. So maximum normal stress acting in this cross section is. Actually, I said that it's a pure torsion case and this will be 0, tau and 0. So for this case, maximum normal stress is equal to given by tau, minimum normal stress is equal to given by minus tau, and maximum shear stress is also given by tau here. So they are asking regarding this value. Understand, anyhow we got the value of tau is equal to 16t by pi d cube for a solid shaft. So sigma 1 answer will be is equal to 16t by pi d cube here. Understand? So that's why we have studied regarding the second chapter. Although like it's not true that what are the stresses and strains which we see on the outer sides on the planes, those are actually the maximum or minimum values there. So we have to analyze the whole body. That's what we have done in our second chapter. So the member, that means we have to find out the maximum stress inside the material in all the planes, about all the axes there. All the infinite number of planes, we have to find out the maximum stress which is occurring there. From that we have to find out here. So maximum normal stress is occurring at this value is equal to given by 16t by pi d cube here. Understand? Understood? So now this is the question here. So use your brain. Although the question is formula based only, but for giving the answer, giving the final answer, you must be using your brain. So but anyhow I have explained you all these things. So recapitulate what I have told you and take care of that part and get the correct answer. Okay. See here, in this one, two limits are given. One thing is regarding the stress, other one is regarding the angle here. First of all, basically, I will take the numerical data given in the question here. It's given that a shaft is transmitting a power of 97.5 kilowatts. So power is equal to given by 97.5 kilowatts, and N is equal to 180 RPM. From this one you can easily get the value of torque. So basically power is equal to 2 pi nt by 60. You can get the value of torque here. Now the remaining part here, the allowable shear stress inside the material is. So tau max must not be going beyond 60 megapascal. So maximum shear stress should be 60 megapascal here. If the suitable diameter for the shaft, okay, find the suitable diameter for the shaft here. The shaft is not to twist more than 1 degree. So theta max is also given here. It is 1 degree. So that means pi by 180. Because we have to take in terms of radians here, it is pi by 180 here. In a length of 3 meters. So length is equal to given by 3 meters here. So in this one, G is also given here. G is equal to 80 into 10 power of 3 into 10 power of 6 Newton per meter square here. Here we have the formula T by J is equal to tau by R is equal to G theta by L. I said that our torque will be creating a shear stress of tau. Torque will be creating a theta of angle of theta here. Understand? So if you take the first one, you will get the answer of diameter. That means T by J is equal to tau by R means you will get the particular value of diameter which will not be allowing. That means like if your diameter is below that value, because if you simplify this formula here, finally you're going to get shear stress as 16t by pi d cube. So tau is inversely proportional to d cube. So if your diameter value is still more increased, that means from this one I guess you should be getting the answer as 76 mm here, around 76 mm. So this says that if my diameter is going below 76 mm, here, so your shear stress will be going beyond 60 megapascal here. Understand? So according to this one, diameter must be greater than or equal to 76 mm here. according to this one here. So you can't go below 76 mm here, because if you go below, if you're decreasing the value of diameter d, tau will be increased here. Understand? This is the one thing. So if you go with the remaining one, that means second equation, second limit here. So tau by r is equal to given as g theta by L here. So tau by r is equal to g theta by L here. So in this case here, from this one, if you do the calculations here, where theta is given as 1 degree here. So theta is inversely proportional to r. Theta is inversely proportional to r. From this one, you get the value of diameter as you're going to get the diameter as 103. I think, yeah, out of 257 here, 103 around mm will be coming here. Whatever you got it here. Understand? So if you, that means diameter is it is given here. So if you take the radius, that means, so if you take the diameter here, so if you decrease the diameter, that means if you decrease the diameter below 103, that means if you go below 103 here, so what happens here? If you decrease the diameter, theta will be increased here. So theta will be going beyond 1 degree here. So according to this one, diameter should be greater than or equal to 103 mm here. Understand? Some people got the answer as 257. Okay, that thing you will be getting if you take, sorry, just a minute. Mistake is there. You should not be taking these two here. It's a big problem mistake here. You should be taking these two. One dependent one, one dependent one, and another independent one here. So if you take these two, then you're gonna get like this. So T by J is equal to G theta by L. So J is having d power of 4 here. So theta is inversely proportional to d power of 4. So according to this one, you're gonna get the diameter as 103 mm. Understand? So that means if you increase the diameter, theta, if you increase the diameter, that means like if you 103, if you go beyond the value, higher value here, theta will be decreased. So theta is decreasing means it's the safer values here. Understand? If you decrease the diameter, theta will be increasing there. So only thing is you can increase the diameter of above 103 mm here. Understand? Some people got the answer as 257. That what are the other value you got it here? Understand? So 257, etc. So the thing you will get between these two. That's actually big wrong, because these two are independent things here. You should not be taking this formula to get the value of diameter there. Understand? Clear? So if you take these two cases, so you are expecting your shaft to have shear stress not to maximum beyond 60 megapascal and angle also not to beyond 1 degree here. So the thing which is actually satisfying both the cases is this one only. The diameter which is satisfying both the cases given by 103 mm only. So you take the diameter is equal to 103 mm as the maximum diameter here. Understood? So this is how you're going to solve this question. Clear? So all the previous gate questions are simply based on this formula itself. You take this one or you take the second equation. So based upon the formula only they have the questions. So you don't need to worry regarding that part. Understood? Clear? So now we are entering into the next part, shafts in series part here. In our first chapter, in linear changes, we have gone through a question in this way. A tensile member is experiencing different loads at different cross sections. So let's take it as P1, let's take it as P2, P3 and P4 here. So for this case, what we have done is, we have taken individual sections like this. If it is A, B, C, D here, we know that each and every member must be experiencing, must be in equilibrium, then only it will be experiencing stress here. So we have gone through in this way here. We have taken the force acting on the section, first one be A, like this one be B here, this one be C here. And we have given the equations here. So at the section B, A is in positive direction, B is in negative direction. Both are giving rise to P2 in positive direction here. So you have got the relation that A minus B is equal to P2, B minus C is equal to P3, C is equal to P4 and minus A is equal to minus P1. So we got all the equations, and from these things we got the value of A, B, C, D, and for the total elongation is equal to given by elongation of AB plus elongation of BC plus elongation of CD here. Understand? So simply like a PL by AE formula will be there. So AL by AE of AB section plus BL by AE of BC section plus CL by AE of CD section. This is the way in which we have solved linear changes problems here. The same thing is there in torsional changes problems here. Understand? So in this case, what they're going to do is, so if you see the diagram of the slide here, they are given a shaft here, which is of a stepped shaft, which having larger diameter D1 up to the length of L1 here, and of the remaining part here, the diameter is D2. The diameter is D2 here, and here the length is equal to L2 here. Understand? So in this case, we see that at the section C, just like ABCD here, we have A, B, and C here. At the section C, it is experiencing an anti-clockwise torque of T2, and the section B is experiencing clockwise torque of T1 here. The same thing we have to do here. What you're going to do is, we take the individual sections and we're going to put, instead of tensile forces here, we're going to put the positive, that means here the positive force, negative force is there. Positive force, negative force. So positive torque, that means anti-clockwise torque, clockwise torque. Clockwise torque, anti-clockwise torque. Anti-clockwise torque, clockwise torque. Anti-clockwise, clockwise. Understand? So if you take the sections in this way, this is AB and this is BC here. Okay. So on B, anti-clockwise must be there, clockwise. Anti-clockwise, clockwise. There is a torque on this ABB small a, torque acting on the BCB small b here. Understand? So we have taken that counterclockwise is positive and clockwise is negative here. At the section B, A and B are giving rise to T1 in clockwise direction. So the formula will become A anti-clockwise here, B clockwise here is equal to, this is clockwise, so minus T1 here. In the same way, if you take section C here, at this case, B is there, so B is anti-clockwise, T2 is also anti-clockwise here. You got B is equal to T2 here. From this one, you can easily get the value of A and also B here. Now, if they ask you what is the angle of twist at the free end, just like equivalent to total elongation of the bar here. So it's nothing but theta at free end is equal to theta of AB plus theta of BC here. So theta of AB, formula is there, we have the angle formula is given by T by J is equal to G theta by L. So theta is equal to given by TL by G into J. TL by G into J. So TL by G into J, if you take it, so T for this section is equal to A into L by G into J for the section AB plus B into L by G into J for the section BC. So if you substitute the values here, you're going to get the answer. Understand? Just like in this case, we have taken care of the sign of the force. That means if any force is coming as negative here, that means that that elongation, that change of length will be compressive in nature. So if you take the force B in or any of them which is coming as negative in terms of sign, so automatically they will be added algebraically here. In the same way, whenever you are getting the values of torques, like ABC value, whichever you are getting in terms of negative sign there, so you have to substitute along with the sign itself. If you substitute along with the sign here, so these angles will be algebraically added and net angle will be shown on the right side there. So final answer, if you are getting it as negative, that means it is rotating. The free end is rotating in clockwise direction. If it is coming as positive, that means you are rotating or creating the effect of rotation on the free end in like if it is positive means anti-clockwise sense, clockwise means negative sign there. Understand? Dear Darwin guys, in this case torque will not remain same. I'm going to show you another series arrangement where you're going to observe a different thing there. This is the first section of shafts in series here. Another section is also there. From after completing that part, you'll come to know there. Understand? So torque will not be same in all these cases. Torque is applied, external torque is applied to section B and section C, so that will be giving rise to different torque at section AB. A will be different with BC. A will be different with B here. Understand? Clear? See here, we are following one sign convention, which I already told you there. Counterclockwise, positive. Clockwise, negative. We are following this sign convention for the torque. So the same sign convention will come for the angle also. Because theta is equal to TL by GJ. So only theta is depending upon the theta value. Theta sign is depending upon the torque itself. Because G, J, L all are positive only. Understand? They cannot be negative. Length, rigidity modulus and polar moment of inertia there. Okay, so counterclockwise sense means positive. Clockwise sense will be taken as negative here. So if you're getting it as positive means counterclockwise rotation of the free end here. If you're getting negative means clockwise rotation of the free end here. Am I clear to everybody? So based upon this knowledge, we're going to solve one question. So if you're clear with the concept here, so I have given everything with respect to this diagram. So it will be changing with the question here. Understand? So you solve this question. So the options are there in the second slide. Okay, so for this case, if you do the whole analysis for this diagram here or loading case here, so strictly follow this method itself, because if you try to use another technique or get confused with any other thing, then you'll be getting wrong answers. So strictly follow one method. Understand, even for the linear changes which I explained you here, so you the method which I have taken it here, which will be very easy to get the answer. So in this one, a shaft is there, Stepford shaft like this, of a larger diameter as 2D, and here the smaller diameter is given as D here. So in this case, here it is ABC. This is clockwise in nature. Understand? So they have given the torque as clockwise torque here. Now let's take the sections, separate sections. AB here, BC here. So we know that our convention, our way of doing it is taking positive one here, negative, positive, negative here. So let's take it as A on AB and B on BC here. So if you take this one, you're going to get the expression like this. B is anti-clockwise, giving rise to clockwise torque, so minus T. So here, A is positive, B is negative is equal to 0. This implies A is also equal to minus T here. So both are experiencing a torque minus T in, both are experiencing a torque T in clockwise sense here. Understand? So both are negative here. So angle of twist is also negative. That means angle of twist also for the both of them will be in the clockwise sense itself. Clear? So total theta is equal to given by theta of AB plus theta of BC here. So theta is equal to TL by GJ for AB plus TL by GJ for BC here. If you substitute this one here, so theta is equal to given by T value for the first one is A, it is minus T, so minus T into length L. AB is equal to L, G is same in the both the cases, so I'll take it outside. J value, J is equal to pi into 2D whole power of 4 by 32, pi d power by 32, plus again torque is equal to minus T here, and length is equal to given by L by 2, and whole by G is already there, so pi value, J value here, J is equal to pi d power of 4 by 32. So ultimately theta value you're going to get the answer as, you're going to take minus TL by G pi outside, minus TL by G pi outside, you're going to get TL by G pi outside here, 2 power of 4, 2 power of 4 is nothing but 816, so 2 by D plus, here you're going to get 16 by D. So you're going to get as minus TL into 18 by G pi into D here. Understand? So actually in this one, sorry, D power of 4 here, D power of 4. So the angle is coming as negative. So minus T into L into 18 by G pi D power of 4. So angle is coming as negative here. So it means the clockwise rotation here. So anyhow they are asking regarding the diameter D value here. So D will come as, so anyhow sign is showing you the direction itself. It's nothing to tell with the magnitude here. So magnitude of D which is required is equal to given by 18 TL by G pi theta whole power of 1 by 4 here. So answer will be given by B here. I hope everything is clear to all. Any doubt is there in this one, everybody? So remaining all the questions with the previous gate are similar to this one itself. So if you are clear with this question, you can solve each and every question. Okay, so those things you can do on your own. Understand? So now in this series, shafts and series case only, we are having indeterminate problems here. So I will explain that indeterminate case using one example, and later I will give you a question as a question for a practice. Understand? So you copy this question, everybody. Do one thing, you just read the question. I will give the solution here, and later you can copy both the question and the solution at the same time. Understand? Let's read the question. It's given that a hollow shaft of length L is fixed at the both ends. So the shaft is hollow shaft 1 and it is fixed at the both ends here. Understand? Both ends here, it's of length L here. So it is experiencing a torque T at a distance of L by 3 one end. So the direction of the torque is not given. So let's take the torque as positive torque itself. So the length of L by 3 from the one end here. So this is the length of L by 3 from one end, torque T is experiencing, torque experiences T here. Now, what is the reaction of the torque at the other end of the shaft? So what is the reaction at this part here? Understand? You take this section as A and this section as B here and this section as C here. Understand? these statically determinate cases, so statically indeterminate cases, that means if you try to apply the equilibrium equations, that means net torque is equal to 0, or net torque in this section C is equal to T in anti-clockwise sense and all, that means if you do it in this way, I am briefly explaining this part here, AB and BC, if you go with the same technique, that means on this part it must be A, on this part it must be B. So you get the answer that A minus B is equal to T here. So you have only one equation from static equilibrium here. Understand? That means net torque is equal to value T here. Okay, so only one equation, two unknowns. So you can't get the answer very easily here. Understand? So this is a statically indeterminate case here. So to solve this one, we'll go in other way. We don't follow this method here. Because if you go in this way, according to the positive on the right side and negative on the left side in this way here, you're going to get huge amount of confusion. So instead of this one, what I'm going to do is, I'll give you a simple technique which will be ending up getting an answer very easily here, without any confusion. Understand? So what you're going to do is, in this technique, we forget about the sign convention. That means we don't consider the positive and negative and all these things here. Clockwise to be positive, anti-clockwise to be negative, or reverse things and all these things here. What I'm going to do is, basically, let's observe this case here. I'll show you. So if the shaft is like this, it is fixed on both sides here. So it is fixed here, it is fixed here. So if I apply a torque T like this, at this section T, so what happens is, if a point is there here, that point will be twisted or shifted to this point here. So this line which was initially straight, that will be coming like this. Understand? When it is coming like this, we see that at this section here, at this section of rotation here, we see that the twist theta is same for both the sections. That means theta is same for this case. I am asking regarding the magnitude. Forget about the sign convention here. Theta magnitude is same for the section AC, and also theta magnitude is same for the section CB here. Understand? So theta is same for both the cases. So what I'm going to do is, in these cases, I'm going to show you in this way. I'm going to take the free body diagram in this way here. So it is AC and here it is CB here. So it is in clockwise direction here, anti-clockwise direction from the side here. So I'll take anti-clockwise only in both the sections here. Let's take it as A, let's take it as A. So to create this in equilibrium, it must be in the opposite direction here. Understand? So it must be, sorry, it was different torque here, A here and also A here. Okay, so in this case, so A and B are giving rise to T here. So one equation we got it as T is equal to A plus B here. But we know that at this section, angle of twist is same in both the cases. And this is fixed here, so angle of twist will be occurring at this section itself. So theta formula we have TL by GJ. Okay, so torque for the first one is A into length L of A. So AL by G into J for the section AC is equal to BL by G into J for the section BC here. Understand? So we know the corresponding length G and all these things here. So as J is same, you can easily do it here. Understand? Okay, so if you solve in this way here, you're going to get very easily here. A is equal to A, L is equal to L by 3 here for the section AC, L by 3, GJ both are same. So B into 2L by 3, G into J. So implies A is equal to 2B. So A is equal to 2B here, so T is equal to A plus B. So you can easily get the answer, what is the reaction torque at the other end of the shaft. So basically you have to get the value of B here. I'm extremely sorry. This thing is B here, so you have to get the value of B here. So if you solve the both of them, T is equal to A plus B and A is equal to 2B. So if you substitute here, so T is equal to 2B plus B implies B is equal to T by 3 here. So this is how you're going to solve this question. Understand? Any doubt in this part here, everybody? Just you have to put it in this way here. You forget about the sign convention, everything will become easy. If you take care of sign convention there, then it will create huge amount of mess. Okay, I don't want you people to go into the mess and waste your time. Okay? Clear, everybody? So if you haven't copied this question, first of all, you give the space and then copy the solution here. After that, you just go and copy this question and get the answer. So these are the options here. You can check. So in this one, we are going to forget regarding the sign convention. Okay, clockwise, anti-clockwise, all these things we forgot here. So when you take a indeterminate case here, so what you're going to do is, you're going to put it in this way. So at the section where the torque is acting, we take the both of them in the same side here. Okay, so in the same direction of the applied torque here. So opposite torques will be there here at the other sections. So T is giving rise to A plus B. So T is like out of T value, so some part is there on the left part, some part is there on the right part here. T is equal to A plus B here. So in this case, we observe that angle of twist will be same in the both the sections. So we're going to take the angle of twist to be same in the both the sections. So that will be the compatibility situation. So that gives rise to this formula here. So using these two equations, you can get the value of corresponding torques, you can get the answer here. Okay. So Hubli guys and Ankit has given the answer as B. So remaining people, remaining 5 people, are you having any problem in this one? Shall I give you some more time to solve this one? This question? So the only difference between the earlier question and this question is, in this question they asked regarding only the torque value here. In this question they are asking regarding the stress value. So you find out which section, that means AC part or BC part, which is experiencing larger value of torque. So whichever is experiencing larger value of torque, that will be experiencing more amount of stress, shear stress there. So correspond to that value of the torque value, you have to get the value of shear stress. That's it. How you are making it equal? See here this diagram. This really happens there. It's a compatible situation there. Understand? So if a torque is applied here, the torque will be creating same amount of angle in the both the sections here. That's why we have to take it. That's occurring here. I'm not taking some approximation here. Okay, this question I'm solving it here. The diagram of this question is in this way. The length is L by 4 here, and this one is 3L by 4. The torque is acting in, it is shown as clockwise here. So it is acting in clockwise direction here. The torque is acting in clockwise direction here. The torque value is called T naught here. Understand? So in this one, you can apply the same concept here. So the torque is acting in clockwise direction. So we'll put all of them in the same way here. So the torques which are produced on the different sections will be on these sections. C section should be in the same direction here. So clockwise here. Clockwise. So this will become anti-clockwise, this will become anti-clockwise here. So let's take on the section AB, the torque is equal to A. Section BC, the torque is equal to B here. So you have T naught is equal to A plus B. Okay, and this A will be creating, that means angle of twist because of torque A on the section C will be same on the section C also. So we have the formula theta is equal to TL by G into J, as G and J both are same in throughout the line. G is same, J is also same here, so we'll take only T into L. So, okay, so T1 L1 by G1 J1 is equal to T2 L2 by G2 J2 here. Okay, so from this one, T1 is equal to A, length L1 is equal to L by 4. Okay, so G into J is equal to T2 is equal to B, 3L by 4 by G into J here. If you simplify this one, you're gonna get the relation that A is equal to 3B. You got A is equal to 3B and T naught is equal to A plus B. So let's get the value of A and B individual in terms of T naught here. Okay, so A is equal to 3B, so T naught is equal to 4B implies B is equal to T naught by 4. Understand? So this implies that B is equal to how much here? T naught by 4. A is equal to then given by 3 T naught by 4 here. So you got the two values of torque. That means the section AC is experiencing a torque of T naught by 4. Section BC is experiencing a torque of given by 3 T naught by 4 here. So as both the shafts are geometrically same, anyhow, both are parts of the same shaft itself. So whichever is experiencing larger value of torque, that will be experiencing larger value of shear stress. Because the formula for shear stress for a solid shaft is equal to given by 16T by pi d cube. In both the sections, diameter is same. So whichever is experiencing larger value of torque, that will be experiencing larger value of shear stress. So section 3 T naught by 4 is higher here. So AC will be experiencing maximum shear stress. Tau max is equal to 16 into 3 T naught by 4 whole by pi d cube here. So it will become 12 T naught by pi d cube. Understand? So 12 T naught by pi d cube here. Okay, so this is the answer here. Maximum shear stress in the shaft is equal to 12 T naught by pi d cube. If they ask regarding minimum shear stress, then instead of substituting 3 T naught by 4, you are going to substitute only 3 here. Understand? So this will become 4 T naught by pi d cube. So the option D is the minimum shear stress inside the shaft here, which is experiencing torque in statically indeterminate way here. Understand? Clear? Any doubt in this one? So copy the solution here. So the last section of this one, last but one section of this section here, shafts in parallel. So once we complete this one, we'll go into the comparison between hollow shaft and the solid shaft. I said while explaining regarding the polar section modulus that polar sectional modulus that. So we're going to compare between hollow shaft and solid shaft, and we're going to decide which one is better one there. Okay. How it is statically indeterminate? Take this equation. Okay. It is the equilibrium equation in terms of moment. That means net moment about the section C is equal to 0. That means if you take the section C in this way here, so A is acting in clockwise direction, B is also acting in clockwise direction, and T0 is acting in anti-clockwise direction here. Understand? So the net moment about this point is equal to 0. In this one there are no force in x and y direction. So only one equation is there, which is from equation of static equilibrium is T0 is equal to A plus B. Understand? We got only one equation from equilibrium of static equilibrium. Okay, but one equation is there, but two unknowns are there. Okay, so we need extra equation to get the values of A and B. That extra equation is coming from compatibility that the angle of twist should be same at the section C, either on the section AC or if you are taking section on the BC here. So this is nothing but statically indeterminate case itself. Am I clear to all? Simply understand that if you in the torsion of the stepped shaft or torsion of the shafts in series here, basically you're going to experience shaft in series here. You're going to experience the numericals as statically determined in nature if they are in this way, earlier way here, like this one. The diagram in this slide here. Okay, so if they are having in this way, that means two fixed supports are there on the both ends of the shaft. So it's nothing but indeterminate case itself. Clear? So everybody clear regarding this concept here? Understand? So I'll complete this torsion topic and give you a break here for you all people. I've already taken a long break. Okay. So is it over, everybody? Shall I go to the next concept? Okay. This was very simple here. So we don't have any questions also in the previous gate papers. So shafts in parallel means basically the idea we get is we have to put one shaft and other shaft both are parallel in this way here. Okay, so like this way here. If you put in this way and if you try to apply torsion like this, understand, this is a very very complex thing here. Understand? So actually if you apply the torsion in this way, which are shafts are parallel in nature, instead of creating torsion, what's happening is they're experiencing bending basically. Understand? So this is not the way in which dealing with this shafts in parallel in the subject of torsion here. So you have to go in the other way here. So basically only one solution will come to put two shafts in torsion and two shafts in parallel and create some torsion here. There is nothing but inserting a hollow shaft inside inserting a solid shaft inside a hollow shaft there. So if it is the solid shaft here, it is inside the hollow shaft here. So this composite shaft, that means it's actually looking like a single shaft itself, because from the outer side we can just see the only hollow shaft here. But inside the gap of the hollow shaft, inside the internal diameter of the hollow shaft there is a solid shaft of the same diameter there. Okay, that means which is equal to the internal diameter of this part here. So this shaft is experiencing torsion. Understand? This total composite shaft is experiencing torsion here. So when it's experiencing torsion, here. So the torque value which is applied given by T here. Let's assume that the torque induced on the solid shaft to be Ts and the torque induced on the hollow shaft be Th here. Okay, so from our equation of static equilibrium we can say that T must be equal to Ts plus Th, because if you superimpose all these things here, Ts is being induced on this solid shaft here and Th has been induced on the solid shaft here. So T is giving rise to both of them. So Th plus Ts must be equal to T here. So this is only one equation which you are getting from equilibrium case. Understand? So one equation but two unknowns. One equation but two unknowns. So this is also a statically indeterminate case here. Understand? So we need a compatibility equation. So the compatibility equation which you will observe here is the same thing as the earlier case here. The angle of twist is same in both the cases. Understand? So TH, TL by A, so TL by GJ for the hollow shaft must be equal to TL by GJ for the solid shaft here. Okay, so theta hollow is equal to theta solid here. This implies TL by GJ this one here. So using these two relations you can easily get it. Understand? So nothing complex in this question here. Simply I understand that. So addition of torques will be addition of torques on the solid and hollow shaft will be giving rise to the net torque applied there, and angle of twist should be same in both the shafts here. That's the only thing which you have to understand here. Okay, so anyhow, we don't have any gate questions in this part here. So we'll be going into the next part here. Regarding this one, everybody is clear? Any doubt is there? Just like a thin cylinder, this torsion is also easy. It's not that much complex here. Okay. So after this one gate question is there. This completes our, only one gate question. This completes our subject of torsion. Okay. Listen carefully here. Let's assume I'm having 1 kg of some metal. Okay. My choice is I can make either a solid shaft or also hollow shaft here. Understand? 1 kg of metal is there. Now I'm going to compare between like what is the advantage I'm going to get if I make a solid shaft, or if there is an advantage if I'm going to make a hollow shaft there. Understand? So here my condition is same weight is there. Same weight in the sense basically like I'm taking 1 kg. So to do the comparison, what I'm going to do is I take 1 kg in one side and other kg in one side. So with 1 kg of one side of the metal, I'm going to make a hollow shaft, and with other kg I'm going to make a solid shaft there. So both are of like constant mass is there. So both are of having same amount of mass. Hollow shaft and the solid shaft here. And other condition I'm telling is I'm taking is length here. Understand? Length must be same in both the cases. Okay. So basically if I make the same weight to be there, so mass is same in both the cases, m1 is equal to m2, but mass can be written as density into volume. Okay, so rho1 v1 is equal to rho2 v2. When both are made up of same material, density will be remaining same. So volume must be equal here, but I am taking length must be equal. Okay. So length must be equal. This implies that area of cross section for both the cases must be same. Understand? That means if you take a solid shaft of diameter d, on one side if you make a solid shaft of diameter d, and hollow shaft which is having a internal diameter as let's take this one as d2 here and outer diameter as d1 here. So area of cross section must be same. So using this one, we're gonna get a result that, please write down everything simultaneously here. Simultaneously everything with me here. A1 is equal to A2. So area pi d square by 4 must be equal to pi by 4 of d1 square minus d2 square here. That means you get a result that d square must be equal to d1 square minus d2 square here. So this thing must be followed in this case here. Okay, so now let me compare between solid shaft and the hollow shaft here in terms of torsion. So if you take the formula for torsion, T by J is equal to tau by R. So basically we get the shear stress is equal to T by Z. Understand? So in both the cases, I'm going to apply same torque value. Understand? So same torque value. So T is same in both the cases. So we get the value of shear stress. We can understand that value of shear stress is just depending upon the polar section modulus of Z here. Understand? So whichever is having higher value of Z, that will be experiencing lesser value of shear stress here. Okay. So I'm going to compare the polar section modulus of Z. Tau is equal to T by Z here, Z for the hollow shaft and the solid shaft here. So I will take a solid shaft here and the hollow shaft here. So Z for the solid shaft is equal to, simply Z is equal to J by R maximum here. So J for the solid shaft is equal to pi d per 4 by 32 whole by R maximum. It is D by 2 here. So in this case, hollow shaft it will become, in the hollow shaft, J is equal to pi by 32 whole into d1 power of 4 minus d2 power of 4 here. So the maximum radius is equal to given by d1 by 2 here. Understand? If we simplify this one, we can remove pi by 32, 2 here. So finally we are going to get the relation that d cube is equal to given by, so I am doing the comparison here, so I am putting on equal to here. So d cube is not equal to d1 power of 4 minus d2 power of 4 by d1. Understand? d1 power of 4 minus d2 power of 4 by d1 here. In this one, d square is equal to d1 square minus d2 square. Clear? So this thing I can write as d1 square minus d2 square whole into d1 square plus d2 square whole by d1 here. So what happens is this d square will be getting cancelled, d1 square minus d2 square here. So d square will be getting cancelled here. So d not equal to d1 square plus d2 square whole by d1. You gotta get this relation here. Understand? So d square will be getting cancelling this one here, d square will be cancelling this part here, so you get the relation here. Understand? If you take any values, that means like like you take some values here which are satisfying this part here. You take d1 is equal to 2, d2 is equal to 1. It will become 4 minus 1, root 3. D is equal to root 3 here. Understand? You take some values and you check this one here. You can observe that this part is higher, Z is higher here. Understand? That means my result is Z for solid shaft is less than Z for hollow shaft here. Z for the solid shaft is less than Z for the hollow shaft here. Understand? So from this one I will get a very important result. The result is, please make it fast. So finally you're going to get this result. Z of the solid shaft will be less than Z of the hollow shaft. So we got the result that Z of the solid shaft is lesser than Z of the hollow shaft. So finally the result is Z of the solid is less than Z of the hollow here. So basically we have the formula tau is equal to T by Z here. So in this one I can say first result, for constant torque, that means in both the cases if I will apply same torque here, for constant torque, tau hollow is less than tau solid. That means when constant torque is there, as Z of the hollow is greater than Z of the solid here, so shear stress, the stress induced inside the hollow shaft is lesser than solid shaft here. It's very important result here. So stress induced is lesser here, so you can use the particular hollow shaft here. You can for the higher value of torques there. Understand? That's the meaning of this one here. And for the second one here, so if you take any material, okay, you can take any material. So like that material will be having some strength that automatically comes from the experiments there. Okay, so we can't change the value of the strength of the material. Okay, if you would like to change the strength of the material, you have to go with some cold working, hard working and all these process there. Okay, so those things we are not going to study in this chapter of SOM here. So basically we understand that at room temperature, if you do the experiment here, so the room temperature, if you do the experiment here, we'll come to know at what value of stress it's gonna fail there. Okay, so this maximum value of tau max is actually fixed here. So anyhow, in this case, you are comparing between two same materials, hollow shaft and solid shaft here. So this thing is constant. So maximum value is constant here. So for maximum stress, for maximum constant stress, or simply because strength may not be every time maximum stress there. So for constant strength here, so torque carrying capacity of hollow is greater than torque carrying capacity of the solid here. So we see that these two results are favoring the hollow shaft itself. So torque carrying capacity is higher, although they are both interrelated with each other here. So torque transporting capacity is higher and stress induced is lesser here. So it is preferred to make a hollow shaft than a solid shaft. Clear? Understand? So this is how this Z value is actually affecting here. So this is Z is having that amount of significance here. Okay? Clear everybody? So if you are clear with this explanation here, another simple example is there. Simple question from GATE 2015 paper. It's not the same case as we have discussed here. It's a little bit different. So you have to take the conditions in the question. So it's given that two circular shafts made up of same material, one is solid shaft, another one is a hollow shaft here. So have a same length and polar moment of inertia. So let's take the solid shaft to be a diameter of D and hollow shaft to be the diameter of this is D1 and D2. So our diameter is D1, inner diameter is D2 here. So both are having same length. So L hollow is equal to L solid here and sectional modulus is also same. So pi d power of 4 by 32 is equal to pi by 32 whole power of D1 power of 4 minus D2 power of 4 here. So in this case this is the condition. So D power of 4 is equal to D1 power of 4 minus D2 power of 4. Understand? Now in this one they are asking us, so both are subject to same amount of torque. So torque is same. Torque is same here. Same torque here. Theta is the angle of twist and tau s is the maximum shear stress in the solid shaft here. So theta h and tau s are corresponding to the hollow shaft. So which of the following is true? So we have to see the comparison between angle of twist and the shear stress here. So for angle of twist here, we have T by J is equal to G theta by L. So theta is equal to TL by G into J. So if you find out, compare between both of them, torque is same in both the cases, length is same in both the cases, G is same in both the cases, J is same in both the cases. So simply we can say theta is same in both the cases. So theta H is equal to theta S. So that eliminates the options B and C. So only option A or D is correct here. Now regarding the shear stress. So regarding the shear stress here, we're going to use the formula T by J is equal to tau by R. So tau is equal to TR by J here, shear stress. So tau hollow is equal to given by torque into hollow shaft. Hollow shaft maximum radius is equal to given by D1 by 2 whole by J. So J is same in both the cases. We're going to compare between them here. So tau solid is equal to given by, so tau solid is equal to given by TR by J. So torque into radius is equal to D by 2 whole by J here. So this is the relation here. In this one, J is same in both the case, torque is same in both the case. So D1, so whichever is having this D1 or D, so D1 not equal to D, so that thing you have to take care here. So if you see from this expression, it is clearly evident that D1 is greater than D here. D1 is greater than D here, because you have to subtract some value to get the value of D. That means D1 is actually greater than D here. D1 is actually greater than D here. So D1 is greater than D means shear stress tau H is actually greater than tau solid here. That gives you answer as D here. Understood? So this is how you're going to solve this question. Clear? Understood?